We're looking at electrolytes here, which is a term we've heard before. An electrolyte is going to be a substance that dissociates or ionizes into aqueous ions when you add it to water, and it will conduct electricity when you dissolve it in water. So you may have seen a video where you can send electricity through an electrolyte solution and a light bulb lights up because the current is able to be connected through the electrolyte solution. So this is an electrolyte here at a particle level, lots of ions that are free and can move around and conduct electricity. So over here, number 1 is what we call a strong electrolyte. The other extreme from that would be number 3 over here, where in beaker 3 you can see that there's no ions. And this is a compound that we saw before was ethanol. It dissolves in water, but it doesn't form any ions. Over here, in contrast, is sodium chloride, and sodium chloride in water, we know from writing our net ionic equations, is actually truly just ions. So an electrolyte is all ions, a non-electrolyte is maybe dissolved, but still neutral. So number 3 here would be non-electrolytes. So let's start with the non-electrolytes. These are going to be most molecular compounds. So you can see up here these large ethanol molecules that dissolved in water would be one example, or these could be, say, oxygen molecules that are dissolved in water. That's like how fish breathe, for example, is oxygen dissolved in water. There are no ions here at all. Now, it's only most molecular compounds because we'll see acids and bases are an exception to that, but we'll get to that in a minute. Strong electrolytes, all we have is, so our non-electrolytes, let's just add to this, we have the no ions at all, right? So on strong electrolytes, we have only ions. So we don't have any molecules or things that are stuck together still. So only ions present. Couple ways we can get a strong electrolyte. We can have an ionic compound, for example, sodium chloride that dissolves entirely, or one of those ionic compounds could be, say, sodium hydroxide, all ions, Na+, and hydroxide, so that would be a strong base. And then we could also look at our strong acids here too. A strong acid would be something like our HCl, that when we added it to water, we got all H+ aqueous and Cl- aqueous. And so we had complete ionization. That's what that forward arrow says. And so up here, this would be like H+ and Cl-, H+ and Cl-. There's no HCl molecules stuck together anymore. So I would say that this goes to 100% completion. It's all going to be ions, and those would be our strong acids. Now in the middle is a spectrum, right? We can all ions, no ions, and then something in the middle, and that's usually how life works, right? You get something in the middle is always an option also. So here in the middle, what we have is a weak electrolyte solution, or weak electrolytes. Those are going to be electrolytes, but not quite as strong. Should remind you maybe of our weak acids and our weak bases. So here, we're going to see some ions present, not no ions, not only ions, but in between. And the compounds that fit in this middle beaker would be weak acids and also weak bases. So we've got the acids and the bases that we're interested in this chapter. So for example, hydrofluoric acid is a weak acid. So we could have HF, put it into water, and it breaks apart into H+ and F- ions. Now, there are constants that tell us how much of this dissociates, but it's going to be maybe roughly 90% molecules and only 10% ions. And so these weak electrolytes, if you read over here, will conduct some electric current, but not nearly as much as my strong electrolyte. So if I look at this picture, these would be HF molecules, and then I would have some F- and some H+, but I have quite a few molecules still stuck together. One last thing I can do with these weak electrolytes is I can actually tie this to chapter 12 and write an equilibrium expression. This time I call it, instead of KEQ, I call it KA because it's for an acid. And if you remember with those, we always put product concentrations over reactant concentrations. So I could say the concentration of H plus times the concentration of F minus. Coefficient is 1 on both of those. So that means that I'm going to have exponents of 1. And then over products, so the concentration of HF. And again, the coefficient here is 1, so the coefficient there would be 1. So we talk a lot when we work on acid-base chemistry about these KAs, and that helps us understand how the equilibrium is shifting with an acidic or basic environment. So be able to define our electrolytes, recognize them at a particle level, talk about them with words, and then also connect them to our diagrams down here. And just to remind you, we're going to see those equilibrium arrows and be able to write an equilibrium expression if we've got a weak electrolyte, a weak acid or weak base. Just for practice, I'll leave you with a few compounds here to sort into the following compounds. So that's another way that you might work on these. Is it a non-electrolyte? Is it a weak acid or base, weak electrolyte? And is it ionic or a strong acid or base over here on the left?